So in question letter C, we're going to start to level up a bit and look at an example that has a bit more going on. But the same two steps still apply. We still need to switch x and y and then get y by itself. So let's start with that same tenet. First, switch x and y. The problem will now say x equals log base 6 of parentheses y plus 1. Notice we don't change anything about the question except the literal placements of the letters x and y. Now I want to get y by itself. And this is where I have to think for a second. I have to use my best algebra instincts here. To get y by itself means that we have to focus on whatever is furthest away from y, get rid of it, and then work our way in. Since y is in parentheses, that seems to imply that the plus 1 is like the last thing I should be dealing with. Y plus 1 is kind of all clumped together, so I need to get rid of whatever's outside the parentheses first before I can work my way in, closer to the letter y that we're trying to solve for. So I need to get rid of a log. And hopefully by now you know that to get rid of a log, we have to use exponential form. You can switch the order if you want to, so that it looks a little bit more like all the other exponentials that we did throughout the page. Some of you may be finding that you can go backwards without having to write the log on the left-hand side. Again, it's up to you. But if you need that familiar structure, you can even draw the little arrow and you can narrate the structure to yourself. It's going to be a base of 6 to the power of whatever's on the opposite side of the equal sign, so x, equals whatever's attached to the log, which in this case is a whole quantity, y plus 1. I didn't put the parentheses, but you can put the parentheses if you want to. The good news, now that I see this, is that y is almost by itself. It's got a plus 1 that we need to get rid of, but that's okay. We know how to get rid of plus 1. Plus 1, its opposite is going to be minus 1, so we can just subtract to both sides. It is worth noting, of course, on the right-hand side, 6 to the power of x is exponential. Minus 1 is not exponential. Those are not like terms. So the best I can do is write it as 6 to the x minus 1. And that's fine. That is actually the correct answer. Y equals 6 to the power of x minus 1 afterwards. So, the moral of the story is simply that as you're learning logs, you're trying to put them in context by reminding yourselves they exist so that they can be the opposites of exponential things. Anytime you have something exponential, a log will get rid of it. Just as anytime you have a log, an exponential will get rid of it. Let's do one more example just to make sure that you can see it, and then hopefully you can spend some time practicing this idea. In question letter D, same two steps. Switch x and y, then get y by itself. So let's look at what that will look like. First step, switch x and y. That means the problem becomes x equals 5 to the power of 2y. Now I want to get y by itself. So I'm looking at things and I'm asking myself, okay, in what order do I tackle this? The 2 is very close to the y, which means that's probably going to be my last step. We always work our way outside, or from the outside in, which means we go for the things that are furthest from y first, get rid of them, and then work our way in. So I need to get rid of this 5. This 5 is exponentiating, which means to get rid of it, I need to write it as a log. That's the only way to get rid of something exponential, is to write it as a log. So I'll have log, and then I'll need to think about the order of things. It has to be log base 5 of something equals the power. So I know that 2y was the power, that means it's going to go there, and x was the leftover bit, so that's going to go there. Again, if you're still not sure how I'm piecing this together, it's from experience. It's mostly because I've seen the pattern so many times that I just kind of instinctively know what goes where. And I can't really say that that's something that by now, after one day of learning logs, you should totally have down pat. So my suggestion is just draw the little arrow that you're used to and piece it together until you can say to yourself 5 to the power of 2y equals x, and then say, oh, right, that's what I just had. 5 to the power of 2y equals x, and you can kind of build the pattern once you start to realize what goes where. The two key pieces are the x and the 2y. So now that you have their positions, notice what you've got. Y is almost by itself. That's what we wanted. We wanted y by itself. All we have to do is get rid of the 2. The 2 is multiplying the y. That's a pretty standard operation. We know to get rid of multiplication, we can divide. And since I'm dividing the right side by 2, I have to divide the left side by 2, which does certainly make for a funkier looking problem, but we can totally write that as our answer. Y is by itself, so y equals log base 5 of x, all divided by 2. And again, that is correct. If you want to graph it, you can verify it to yourself, or you can check the answer key. I'll leave that up to you. If you can, try to do as many of the remaining problems as possible. If you get a tricky one, it's okay to skip. That's certainly fine. But try, if you can, to start to put into context, why would we even use logs in the first place? Namely, what do they accomplish? And that, of course, is answered by going back to this idea of opposite. Logs are going to be added to our arsenal of opposites. We know subtracting is the opposite of adding, square is the opposite of square root, multiplying is the opposite of dividing, and now we know that logs are the opposite of exponential. So, to tie this together, think about this idea of opposites. Practice doing these inverse problems because it really forces the idea of opposites to be front and center in your brain. And once you've established that opposite concept, I think you'll find that the next couple of lessons will make more sense, because now you'll understand why we're doing logs in the first place, why we use them, why they're important, and where they're going to fit into the bigger picture of algebra.